So hello everyone, welcome to this new session. So as you knew that we have not covered module 5 and all of you were waiting for this module 5 video, right? So I'm here with you all for module 5 with the two of the important concepts. One is Bode plot and one is Nyquist plot. Okay, so two separate sessions I'm going to do for those two topics, and I'm going to try to cover the whole concept of Bode plot in one video as well as Nyquist plot in one video. Okay, so this is the first problem. Without wasting any time, we are going to solve the first problem. So the first problem says that draw the Bode plot, determine gain margin, phase margin, gain crossover frequency, phase crossover frequency, and comment on the stability. Okay, so here they have given the simple unity feedback system, that is g of s is equal to 80 divided by s into s plus 2 into s plus 20. So first thing what we should be doing is we should be trying to write it in a general form. That is, general form is this form, that is k into 1 plus t1s divided by s into s power j into 1 plus tas, and it goes on like this. The general form we should be trying to write it. For that case, what I am doing is g of s divided by, here I am taking 2 and 20 outside, so that I would be getting the answer as 2 divided by s into 1 plus s by 2 into 1 plus s by 20, where the values of coefficient of s is here 1 by 2 and coefficient of s is here 1 by 20. Those are the values of t1, t2 and all. Okay, like this we would be getting the g of s in general form. So okay, from this general form equation what we can concluding that here we have 2, right? That 2, that we can write it as k is equal to 2. Okay, since in the general form we have one k term, okay, that k term is represented as k is equal to 2. Okay, and also 1 by s is one pole at origin. That is, 1 by s stands for this, in the denominator by s we have, right? So if we consider 1 by s, that is this 1 by s, and that one pole is at origin. Since we know that s is equal to 0, the whole denominator part, if we equate it to 0, we would be getting the poles. Okay, so that is 1 by s is one pole at origin, and one pole at origin for Bode plot we should be considering the value as minus 20 dB per decade. Okay, for one pole at origin. Okay, similarly for 2 poles, 3 poles, it is minus 40 dB and minus 60 dB per decade. These, how to draw this minus 20 dB, minus 40 dB, minus 60 dB per decade, I am going to explain it when I show you the graph for this problem. Before that, now first what we should be doing is, now 1 divided by 1 plus s by 2, from this g of s equation 1 divided by 1 plus s by 2 I have taken outside. Okay, from this what I can say that the coefficient of s, that is 1 by 2, that is I am taken outside, and that I have named it as t1. Okay, t1 is equal to 1 by 2. From this t1 I am going to get the value of omega c1. Okay, this is first crossover frequency. This is called as first crossover frequency. Okay, that is given as omega c1. Omega c1, we know that the relationship between frequency and time, it is inversely proportional to each other, so that we will be getting 1 by t1, 1 by 1 by 2. Therefore our omega c1 first crossover frequency, we are getting it as 2 radian per second. This we will be marking it in the graph. I will tell you how. Okay, then the next step is for next year, that is 1 divided by 1 plus s by 20. For this again the value of coefficient of s is 1 by 20, so t2 is equal to 1 by 20. Omega c2 second crossover frequency is equal to 1 by t2, that is equal to 20 radian per second. These are the two crossover frequencies. Now we have two main kind of analysis in this Bode plot. One is magnitude plot analysis, and the second one is phase plot analysis. Okay, so let's discuss with magnitude plot analysis now. For this magnitude plot analysis, what we should be doing is take the value of k which you have got initially, that is k is equal to 2, then try to write this k is equal to 2 in decibels. Since in the semi-log graph sheet, the Bode plot we should be representing in decibels. Okay, yeah, so that's why in decibels this value of k should be representing as 20 log k, that is equal to 20 log of 2, that is equal to approximately, it is equal to 6 dB per decade. Okay, this 6 dB per decade is the reference line which you are going to draw in the graph. I am show you this 6 dB per decade reference line, how to draw it in the graph. Okay, when I explain the graph part. So this much is clear for you all. So please, if it's clear, then hit a like for us. Okay, then we should be creating a table like this of term, corner frequency. Okay, that omega c, those and all are the corner frequencies. Then slope, then change in slope. Okay, sorry, this is not a crossover frequency. These and all are the corner frequencies. Okay, by mistakenly I have told it as crossover frequency, it is corner frequency. Okay, omega c1, omega c2 are the corner frequencies. Okay, yeah. Then slope, change in slope. So this table we should be writing in such a way that we should be writing the table in the increasing order of corner frequencies. Okay, in that way you should be writing all the terms, not in just how I've represented like this, not in this way you should be writing. You should be writing the table in terms of ascending order of corner frequency. As you can see that for this term 1 by s we don't have any corner frequency because we don't have any time. Okay, it is not in of the form 1 plus ts. Okay, so that's why we are getting only 1 by s, so no corner frequency. That term you should be writing it first. For that, what is the slope? Minus 20 dB per decade, and change in slope is also initially it is minus 20 dB per decade only, it remains as it is. Then the next ascending smallest corner frequency is 2 radian per second, that we should be writing, and its term, okay, that is how we got this 2 radian per second, by substituting it in this term, that is 1 by 1 plus s by 2. Then its slope is also, since it's again one pole, and one thing we should be keeping in mind, for poles it would be always minus 20 dB per decade. Okay, change in slope. Then for zeros it is always plus 20 dB per decade. Okay, change in slope is always plus 20 dB per decade in case of poles and zeros. Okay, that you would be understanding in brief when we see the graphs. Okay, yeah. Then the change in slope, okay, from minus 20, again if we add minus 20, the change in slope would be minus 40 dB per decade. Again the next corner frequency is 20 radian per second. Its term is 1 by 1 plus s by 20. Its change in slope is, since it's a pole again, okay, that's why the slope is minus 20 dB per decade, and change in slope is from minus 40. If we add minus 20, the change would be minus 60 dB per decade. That only I have written. See, s in the numerator, then it is plus 20 dB slope. S in the denominator, then it is minus 20 dB slope. That only I have told you here, right? So this was one magnitude plot analysis. Next we should be doing the phase plot analysis. For this, what we should be doing is we should be replacing s by j omega. Okay, whatever that wherever s is there, you should be trying to replace it by j omega. That is, once we have 1 by s, so it will be written as 1 by j omega. That we should be representing as tan inverse of what in bracket, what we should be writing in first. Take separately numerator as well as denominator. In case of numerator, tan inverse of imaginary part of numerator divided by real part of numerator, minus tan inverse of imaginary part of denominator minus real part of denominator. For all this we should be doing the same thing. Okay, so here if we see, consider the numerator, we don't have any imaginary term, so it is 0 divided by the real part is 1 minus tan inverse of, in the denominator the imaginary part is j omega, the coefficient of j, that is omega. Okay, that is the imaginary part, divided by no real part, so that's why it is 0. So tan inverse of 0 is 0 minus tan inverse of anything divided by 0 is infinity, so minus tan inverse of infinity. Minus tan inverse of infinity is minus 90 degree, so write that angle as minus 90 degree. Similarly for all of them, do the substitutions. Okay, then we would be getting separate angles. That is, for this one we are getting minus tan inverse of omega by 2, for this one we are getting minus tan inverse of omega by 20. Okay, then we should be taking some frequencies as the table, in the table to add. Okay, we can take it any frequencies. Okay, some 5 to 6 values are enough, and those values you should be considering the values which we have taken the corner frequencies, that is 2 and 20. This must be there in this when we are taking the values. Okay, so that's why I have highlighted this 2 and 20, some random numbers you take. Okay, then what we should be doing is we should be doing a table like this of radian per second omega minus 90, whatever the angles we have got, right? Separately we should be writing it here, whatever angles we have got, it separately write the table for that. One is minus 90, second angle is minus tan inverse of omega by 2, third angle is minus tan inverse of omega by 20, then phi r, this is the total angle. So how to do this table is, take all the frequencies values which I have mentioned, then minus 90 degrees, since we don't have any omega value here, so right in this column first all the terms write it as minus 90 degree, then minus tan inverse of omega by 2. So one by one for all the omega values we should be getting the angles. That is, for the in this first case, if we substitute the value of omega as 0.2 divided by 2 minus tan inverse of 0.2 by 2, you would be getting an angle of minus 5.71 degree. Similarly for omega is equal to 2 radian per second minus 45 degree, and for all the values you would be should be write the values. Since we know that tan inverse of infinity is minus 90 only, so here the in the infinity column all the angles should be minus 90 degree. Similarly for minus tan inverse of omega by 20, substitute the values one by one and write all the angles. Then what we should be doing is we should be adding all these three angles. Okay, in the first row, what and all the angles we have got, add all of them and write it in the final angle as here, the summation of all these three angles. Similarly, like this, for summation of these three angles, write it here, these three angles, write it here, and so on. Okay, this is the final table where we should be plotting these angles in the semi-log graph sheet. Okay, so like this, these are some of the calculations which we should be doing. Now let's get to the graph part. So this is the graph. So how to plot the graph is, some major rules to plot the Bode plot graph I am going to tell you now. That is, this one section is there, right, from here to here. That section is called as one decade. Okay, one decade. And I have just drawn some of the reference line, that is, I have given the scale as, this is the scale for decibels and this is the scale for frequencies omega radian per second. Okay, so here this is of 0.1 radian per second, 0.2, 0.3 up to 1, then we have 1, 2, 3 up to 10, then it is 20, 10, 20, 30 up to 100. Hope you might be knowing this. Hope you all of you have used the semi-log sheet. Then here this is the values for decibels. First thing, when you draw the Bode plot, what we should be doing is one line of 0 dB line 1, then the minus 180 degrees. So from here, in below 0 dB line we should be writing all the angles. Okay, by taking 30 divisions. Okay, one section as this full section as 30 degree. Okay, and you should be writing the angles up to 270 degree. Then draw one 0 dB line, one straight line you should be drawing for 0 dB line, and one straight line you should be drawing for 180 degree. And whatever the reference line which we have got, right, in our calculation, that is 6 dB here in this case. This problem we have got 6 dB, that we should be drawing here. Okay, so here see, I have drawn that line here, 6 dB from if this is 10, this is 2, 4 and this is 6, this is 8 and 10, so this is 6 dB line. Draw that 6 dB line as well. Okay, after that what we should be doing is, I have told you, right, this one whole section is one decade. Draw three of the reference lines. Okay, reference slope lines. One is 20 dB per decade, 40 dB per decade and 60 dB per decade. Okay, so this is 20 dB per decade line, this is 40 dB per decade line, and this is 60 dB per decade line. Okay, like this, all these three reference I have drawn it. Okay, one more thing to calculate, how to calculate slope is, we have one more trick to calculate slope. That is, to calculate any slope, we know that this is one decade, right? So in order to draw this line, what we should do is, from this point draw 20 dB per decade means 1 inch in scale. Okay, 1 inch you draw from here, 1 inch. Okay, that is equal to this, or this to this is 1 inch. Okay, keep it here, and this is 1 decade. So from this point to this point, if you drop one line, that is the slope of 20 dB per decade line. Similarly for 40 dB per decade, from this point keep the scale to 2 inch, and this is 1 dB line. So from this point to this point, if you draw the slope, you would be getting 40 dB. Similarly for 60 dB. Okay, yeah. So now next what we should be doing is, we should be trying to draw the magnitude plot. Okay, so how to draw the magnitude plot? So in the first case, the corner frequency, since we don't have any corner frequency, so we should be starting from 0 radians per second. Okay, from which point we should be starting is, since we have drawn the reference line in 6 dB, okay, from this point we should be drawing one slope of 20 dB per decade. Okay, that is, if this is 6 dB, we should be starting from 26 dB. Since 6 dB to 26 dB, you would be getting 20 dB. Okay, from that we should be drawing one slope of 20 dB per decade. As I've told you, right, from this point take 1 inch in scale, and this is 1 dB per decade, and from this point draw the slope, and this slope we should be drawing till the next corner frequency in the table, that is 2 radian per second. Okay, this slope we should be drawing till we touch 2 radian per second in the graph. Okay, yeah, so here we have touched the 2 radian per second. Okay, till that we should be drawing the 20 dB slope, and if you want, you can extend this slope, no problem. Okay, then where you have touched 2 radians, right, mark that point over here. Okay, and from this 2 radian per second, the change in slope is minus 40 dB per decade. So that's why from this point onwards we should be drawing one slope to minus 40 dB per decade, okay, from 2 radian per second, that is 20 dB per decade. You should be changing from 40 dB per decade, that is from this 2 to the next 2, that is 1 decade. And from this point, if you keep 2 inch in the scale, this is 2 inch, okay, so we can join this to be drawn as the 40 dB per decade line, okay. So that's why draw this 40 dB per decade line till the next frequency, that is 20 radian per second, that is this is 20 radian per second. Till here we should be drawing. You can extend this line, no problem, okay. This is 20 dB per decade line, and after that after 20 dB per decade the slope change is minus 60 dB per decade, okay. So that's why from this point onwards till infinity, since we don't have any other frequency, till infinity, or we can stretch this line till the end to 60 dB per decade, okay. So this was all about magnitude plot. So phase plot is very simple, okay. Since the phase plot angle starts from above 90 degree, what we can do is from 0 write one angle of minus 10 degree, okay. After that skip all the angles and start directly. If you want, you can start directly from minus 90 degree, no problem, okay. Start from minus 90, minus 120 up to 270, write all of them, okay. Then mark see the frequency versus angle graph. For 0.2 the angle is 96.28, mark like this here, 96.28. then for next frequency it is 2, mark the angle like this, mark the points like this, and then join those points using scale, okay. So that we would be getting the phase plot analysis. Now they have asked us to calculate gain crossover frequency and phase crossover frequency, right? Omega GC and omega PC. How to check that in the graph is, we don't need to calculate anything, we should be just knowing what is this gain crossover frequency is. This magnitude plot is there, right, okay, and this is the 0 dB line, okay. Wherever this magnitude plot touches the 0 dB line, right, that point is called as gain crossover frequency, okay. That point you should be checking from that point what is the frequency, and that frequency is called as gain crossover frequency. Similarly, the phase crossover frequency, we have drawn the phase plot, right, in which point, right, it touches the minus 180 degree line, okay, that point, and that point, from that point you should be checking the frequency, okay. We should be drawing one straight line and you should be checking the frequency, and whatever the frequency obtained here, that is called as phase crossover frequency, okay. Like this you should be checking for gain crossover frequency and phase crossover frequency. Now in order to calculate gain margin GM and phase margin PM, what we should be doing is, whatever the gain crossover frequency and phase crossover frequency you have got, right. So for example, we have got gain crossover frequency here as 2 radian per second, okay. From this 2 radian per second we should drop one straight line perpendicular downwards till that line should be touching this 0 dB 180 degree line, okay. Like that we should be drawing this perpendicular line, okay. If you drop this perpendicular line till the 180 degree line, we would be getting the phase margin, that is from this point it touches, right, and then this is the phase plot here. We should be marking this like this, okay. So this perpendicular line and this, from this point up to the point where it touches the phase plot, okay, this region is called as phase margin, okay. And that phase margin you can check it by checking here like this. So here you can see that from here to here it is 30 degree, and from 30 it slightly goes up to 38 degree, okay. So here in this case the phase margin is 38 degree. Similarly, gain margin is the same thing. From phase crossover frequency, whatever we got, drop one straight line till it touches the 0 dB line, okay, and from that 0 dB line up to the magnitude plot wherever it touches, and this region is called as gain margin, okay. That gain margin here in this case is 20 dB. You can check it, since this one region is 10 dB and this is 10 dB, so 10 plus 10 is 20 dB. Like that you should be calculating the gain, you should be marking the gain margin, phase margin, gain crossover frequency and phase crossover frequency. And also they have told us to check the stability, okay. Stability is simple. What we should be doing is, whenever we get the phase crossover frequency as the more than gain crossover frequency, that is whenever we get the phase crossover frequency as the largest value, then we can directly say that system is stable. Whenever we get gain crossover frequency as more than phase crossover frequency, then we can say that system is unstable. Whenever we get gain crossover frequency and phase crossover frequency nearly equal, then we can say that the system is marginally stable, okay. So yeah, this was all about Bode plot, okay. Hope you understood this very carefully, okay. So let's discuss a few more problems related to this Bode plot, okay. So this is one more kind of problem, okay, where this is of different kind. So question is, the open loop transfer function is given by k divided by s into 1 plus 0.02s into 1 plus 0.05s. Draw the asymptotic Bode plot and hence find the value of k, for which the gain margin they have already given it as 10 decibels. What is the corresponding phase margin? Okay, so this is one tricky question and yet very important question. Okay, so that question is first, here we should not be writing reducing this into general form because it is already given in the general form itself. So first thing what you should be doing is try to write the poles, that is 1 by s. This is the first pole at origin, that is minus 20 dB per decade. This is the second pole at origin, minus 1 by 1 plus 0.02s, that is second pole, and 1 by 1 plus 0.05s is the third pole. All are of minus 20 dB per decade since these are poles. Okay, so that's why the change in slope is minus 20 in case of poles, and in case of zeros the change in slope is plus 20. Okay, so now one by one try to find the corner frequencies for all this. Since this is 1 by s, it is not of the form 1 plus ts. We don't have any time, so that's why we cannot calculate any omega. We can consider the value of omega as 0 radian per second. In case of second thing, this is the value of t. Take it as t1. T1 is 0.02, omega C1 is equal to 1 by T1, that is 1 by 0.02, that we are getting it as 50 radian per second. Similarly, if we substitute the value of T2 as 0.05, we would be getting 20 radian per second. So these two are the corner frequencies obtained here. Okay. So for magnitude plot, what we should be doing is, they have told us to find the value of k, right? Okay, but we don't have any value of k, so that's why if you want to convert it in decibels, we don't have any value of k, so 20 log k also we cannot find. So in this case, what we should be doing is, we should consider 0 dB reference line. Okay, that is, we should not be drawing any reference line in this case. In the earlier problem, what I have told you, whatever the k value is there, after substituting it in decibels, that reference line we should be drawing in the plot. Okay, so here in this case, consider 0 dB reference line, that is, we should not be drawing any reference line. Okay, so here then again the same thing, make the column of term, corner frequency, slope, change in slope. Write this term in the ascending order of corner frequencies. Okay, 1 by s, 1 plus like this, write it. Then slope change is slope is for, since all of these are poles, so minus 20 only. Then change in slope is, first is minus 20, then if we add minus 20 again, it would be minus 40. If we add minus 20 again, it would be minus 60. Then again phase plot analysis. Okay, s is replaced by j omega. Then again the same thing, 1 by j omega for numerator, tan inverse of imaginary part by real part, minus for denominator, tan inverse of imaginary part by real part. Substitute it and we would be getting the angles as minus 90 degree, minus tan inverse of omega by 20. Since it is 0.05 omega, we can even write 0.05 as 1 by 20, so I have written it as omega by 20. And this is the third angle, that is minus tan inverse of omega by 50. Then again the same thing, take some of the corner frequencies. Okay, that is 0.2, and we should be taking the values of 20 and 50 compulsorily, that is, I have taken here 20 and 50 in the data, and some 5 to 6 values of frequencies you take. Okay, then all the angles you make column for all the angles which you have got, 90 minus tan inverse of omega by 20 minus tan inverse of omega by 50, then phi r is the phase angle. Okay, and for minus 90 degree, we know that it is, we don't have any omega value, so this we should be keeping as it is. And for infinity value, tan inverse of infinity is minus 90 degree only, so this here 90 degree would be remaining as it is. Then fill all the check all the values for omega for all the different data. Then here we should be adding this, all of them, we should be adding these three things, so that we would be getting the answer of minus 90.8 degree. Similarly, if we add these three, we would be getting 98 degree, and like this we would be getting all the angles for phi r. Okay, and these phase angles you should be drawing in the plot. Okay, so like this the plot would be coming. So here there are many lines here. I would be explaining one by one how I have drawn this. Okay, since in the question they have asked us to find the value of k, right, in this case. So yeah, so here first what we should be doing is, that is, since here this is the 0 dB line, I have told you, one line in 0 dB, one line for minus 180 degree, and mark the angle scale here, that is decibel versus radian per second, like this, mark it. Okay, each division name it as 10 dBs. Okay, so from angle you can start from minus 10, and since the angle starts from above minus 90 degrees, so that's why we can skip other angles and directly start from minus 90, mark it up to 270. Okay, then here what we should be doing is, now first thing, since there is no reference line here, and the the first frequency is 0 radian per second, so that's why we should be starting from 0 radian per second. We should be drawing one 20 dB slope. Okay, I've told you, right, 20 dB slope how to draw. This is 1 decade. Okay, from here mark 1 inch, then draw 120 dB slope. Up to that we should be touching the frequency of 20 radian per second. As you can see here, I've drawn one slope here up to 20 radian per second. So this is 10, this is 10, and this is 20. Okay, till 20 I've drawn. Okay, and from here the slope would be changing to a minus 40 dB per decade. So here draw the slope of minus 40 dB per decade up to 50 radian per second. So you can see that this is 2 and this is 5, so this is 50 radian per second. Then after that you should be drawing the slope of minus 60 dB per decade up to infinity. Okay, so this is all about magnitude plot. And phase plot also is the same thing. What and all the angles you got, beautifully you mark it by checking the omega versus phi r graph. Okay, check all the values of omega and mark the phase plot like this. Then we should be checking for gain margin and phase margin along with gain crossover and phase crossover frequency. So in this question they have not mentioned gain crossover and phase crossover, but yet I am marking it to you all. Okay, so how I told you gain crossover frequency how to calculate, we should be checking for the intersection of 0 dB line, okay, of the magnitude plot. So this is the first initial magnitude plot which I have drawn. Okay, so here this is the intersection point, and that point of intersection is in the 1 radian per second. So this is called as gain crossover frequency. Similarly, the phase plot intersection in the minus 180 dB line is here. Okay, if you check it from here, we will be getting around, this is 3, so 10, 20, 30 and around 32 radian per second. I have marked it as 32 radian per second, that is phase crossover frequency. Okay, so this is all about initial plot. So in initial plot, what the gain margin which you have got from phase crossover frequency, if you draw one perpendicular line to the 0 dB line, and if we check the phase gain margin from here to here, okay, this is the first initial gain margin which I have got, that is 32 dB. Okay, but in the question they have already mentioned the value of gain margin as 10 dB. You can see here, right, 10 dB as they have mentioned. So what we should be doing now is, okay, we should be converting this 32 dB gain margin to 10 dB gain margin by just shifting this whole 32 dB line gain margin, 32 dB gain margin to here. We should be checking for 10 dB. So this one thing is 10 dB, right? So here for this initial magnitude plot, you should be marking 10 dB where it intersects to 10 dB. From that point, we should be marking the 32 dB plot. Okay, gain margin. Okay, from here up to where it touches. Okay, and that where it touches, right, from that point we should be drawing one reference line. So this, from this 10 dB where I've got this 10 dB here, okay, from this point you should be marking the initial gain margin which I've got, that is 32 dB, that where it touches, that from that point you should be drawing one straight line, and this line is called as the new reference line which we have got. Okay, so now since we have got the reference line again, so now what we should be doing is from that reference line again try to draw one final magnitude plot again of the same kind. Just what we should be doing is we should be keeping the scale here, and parallelly we should be drawing one more magnitude plot of the same data. Okay, that is, so here you can see that, so this is the new reference line we have got, and this reference line, since in the initial gain margin we have got it as 32 dB, and we have marked one 10 dB gain margin for this magnitude plot which touches the 0 dB and 10 dB here. This is 10 dB, and if we draw one 32 dB gain margin plot here, so from 0 up to this point the margin which you have got is around 22 dB. So that's why here we are drawing one 22 dB reference line. Okay, so this is the 22 dB reference line we have drawn. So from using this 22 dB reference line, again for the same data try to draw one slope here, start from 0 radian per second, draw one slope, okay, which touches up to 20 radian per second first, then change the slope to 40 dB per decade, and it touches up to 50 radian per second, and from 50 radian per second draw one infinite slope of 60 dB per decade. Okay, so this is the new magnitude plot which I have drawn. Okay, and if you check this new magnitude plot, so here the the gain crossover frequency changes. Okay, for this new magnitude plot it touches the 0 dB line in this point. Okay, so this is the new gain crossover frequency which I have got, that is 11 radian per second. Similarly, for a phase crossover frequency, if you see, okay, phase crossover frequency would remain the same, it won't be changing. That is since it is touching the 180 degree plot here only, so this won't be changing, this would be remaining as it is, that is 32 radian per second. But the gain crossover frequency would be changed because we have shifted the magnitude plot above 22 dB line. Okay, so that's why we are getting new gain crossover frequency. And also if we check the gain margin now, in this case from this point to here, if we draw one perpendicular line from 32 dB line, so this is the new gain margin, and now this is of 10 dB. Okay, since in the question they have mentioned it as the gain margin is 10 dB, so that's why I have marked this in such a way that the gain margin would be, we would be getting it as 10 dB. Okay, so now we have got the gain margin, and now for this they also told us to find the corresponding, what is the corresponding phase margin. Okay, they have mentioned phase margin also, right? So now what we should be doing is, since the initially the phase margin we have got here, we have checked it here, right, from this gain crossover frequency, first gain crossover frequency, whatever we have got, we've dropped one perpendicular line to the 180 dB line, and this here we have got initially a phase margin as 85 degree, but now after we changed the whole magnitude plot, here we have got new gain crossover frequency, and now from this new gain crossover frequency we are drawing one perpendicular line, and here this is the new phase margin which we get here. Okay, this is the new phase margin which you get, and this phase margin is around 36 degree. Okay, so now we have one question is already done, that is phase margin, corresponding phase margin we have already found it as 36 degree. Now what we should be doing is, they have told us to find the value of k, right? So now reference line we have drawn, right, that is reference line is starting at 22 dB as you have seen in the question. So how this 22 dB we get this 22 dB by 20 log of k, right? 20 log of k is equal to 22 dB, that is the reference line. So that's why log of k is equal to 22 by 20, log k is equal to 1.1, then k is equal to, if you want to bring this log to other side, it would be anti-log, right? Anti-log of 1.1, and this anti-log which can be represented as to the base 10. Okay, that is k is equal to 10 to the power 1.1. That is approximately we are getting the answer as 12.589. Okay, so like this we should be finding the value of k. Okay, in this way we should be finding the value of k, and this is the initial phase margin which I have got 85 degree, and the final phase margin from the plot we have seen, right, it is 36 degree. Okay, so this was this very important problem, so please note it down.